We shall get started with very interesting topic, that is differential analysis of fluid flow. Let's go to the slides. So here, see, there are two approaches. So we have finite control volume approach and the differential approach. So if we just see, the finite control volume approach is very practical and useful, but it does not give the detailed knowledge of pressure and velocity variations. But problems could be solved without detailed knowledge of the flow field. That is the strength of the finite control volume approach. However, there are many situations where in which you need detailed flow analysis, like for example flow over a blade, flow around cylinder. You need detailed velocity distributions, or how does velocity vary in the cross section of the pipe. So for that sake you need to take up differential analysis. In the differential analysis, so you see in the control volume, what is happening inside the control volume is a black box. So we don't care about what happens inside. We only worry about what is getting in and getting out. But unlike control volume approach, in the differential analysis, we take up complete flow domain. For example, this is a blade. What is happening to the velocity? What is happening to the pressure? Are there any vortices there? What happens to the velocity gradients? All of that we will be able to capture in the differential analysis, which is not possible in the control volume. So kind of control volume is engineering approach, differential analysis is scientific approach. But it's a loose statement, but nevertheless we can try to understand it that way. Now if I take what happens to my fluid particle, in the next few seconds what am I trying to do is that I will try to model the general motion of the fluid particle. So if you just see what is happening at instant t naught, my fluid particle was square, and at t naught plus delta t, you see what all things it is undergoing? It's undergoing translation, linear deformation, rotation and angular deformation. So you have general motion comprising of translation, linear deformation, rotation, angular deformation. All of them can be there. Translation, in translation you see the shape has not changed, it has just moved from one location to another. In linear deformation, whatever surfaces were perpendicular, they continue to be perpendicular, only thing is that the size has changed. In rotation, there is no deformation, only it has rotated. Neither angular deformation nor linear deformation is there in rotation, it has only rotated. In angular deformation, you see the angle has changed. It was perpendicular here, these two, but here they are no longer perpendicular. So when a fluid motion takes place, the fluid particle undergoes translation, linear deformation, rotation and angular deformation. Now this is translation. So in the translation, what is happening? In the translation, if you just take translation, so you have a particle, let me just write translation, you have the fluid particle, we are visualizing it as a kind of a square O, and you have velocities u, and this is the velocity v in the x and y direction. Now it has moved to a new location after time delta t has elapsed. So what is the distance it has covered in the x direction? It is u delta t. And what is the distance which is covered in the y direction? It is v delta t. This is simple translation. Now let us move on to, back to slides, linear deformation. So that is linear deformation. So let me come back to write up. So if we take up, so let's now start deriving. So linear deformation. So if I draw the square, okay, so this, let us call this as O, A, B and C, and this is delta x, delta y. So what is the velocity here? At O it is u, and what is the velocity at B? It is u. And now what is the velocity here? Here it is u plus del u by del x delta x. How did I write this? I wrote it by Taylor's expansion series, that is f of x plus delta x equal to f of x plus del f of x by del x delta x plus 1 by 2 factorial del squared f of x upon del x squared delta x squared plus higher order terms. So, I am neglecting because delta x is very small. I have taken only u plus del u by del x delta x. Similarly, here the velocity would be u plus del u by del x delta x, del u by del x into delta x. So, what will happen because of this velocity gradient? There is a gradient here u and here it is higher by del u by del x. So, what will happen to my fluid particle O, A, B, C? It would get now stretched in the x direction by how much distance? This distance would be del u by del x delta x into delta t. This is what it is getting stretched. So, A has become now A dash and C has become C prime. So, now what has happened? The stretching of the volume element, the change in the volume element, the change in the volume, the difference or the change in the volume of the fluid element has become equal to del u by del x into delta x, delta y, delta z is same, delta t. Okay. Similarly, if I take, or let me just simplify, let us say stretches they only in the x direction. Now, if I calculate rate of change in volume per unit volume, if I take, that is 1 upon delta V, d of delta V, V is volume, divided by dt. So, that is limit as delta t tends to 0, del u by del x delta x, change in volume is this one, delta x delta y delta z delta t upon dt, and of course, I am having delta x delta y delta z. So, what will happen? Delta x delta y delta z, this gets cancelled out. So, I am left out with del u by del x. So, if there is stretching, in the y direction also, let us say y and z direction. So, what will happen? 1 by delta v, d of delta v by dt equal to del u by del x plus del v by del y plus del w by del z. That means what? Del u by del x is stretching in the x direction and del v by del y is stretching in y direction and del w by del z is stretching in z direction. It can be compression also. If it is compression, then this becomes minus. So, this can be visualized as net dilation rate, how much it is getting dilated. Now, you see, for an incompressible fluid, what will happen? This net dilation rate, if I take incompressible fluid, this net dilation rate, that is del u by del x plus del v by del y plus del w by del z is equal to 0. Why? Because mass is equal to density into volume. Now, for incompressible fluid, density is constant. So, the change in the volume should be 0, which is what is this del u by del x plus del v by del y plus del w by del z is equal to 0 is coming down to. So, in the we are going to come across this term. So let us write this as, in the conservation of mass we are going to get, so we will write this as del u by del x plus del v by del y plus del w by del z is equal to vectorially del dot v, where v is equal to iu plus jv plus kw, where I, j, k are unit vectors. Okay, so now that is so much about the back to slides. If we come back to slides again here, so you have variations in the velocity, in the direction of velocity, that is u in x, v in y, w in z, that is in the same, the velocity in the same direction we are taking, that causes linear deformation. We are going to see next that u in y and z and v in x and z are going to cause rotation or angular deformation. So how does that happen? Let us try to understand. So let us start writing now. So that is, we will start off with angular deformation, motion and deformation. So again I am taking same elemental volume, that is fluid element volume, that is I call that as O, A, B, C, and this is delta x, delta y. What are the velocities? I have velocity u and this is velocity v. Okay, so what would be the velocity here for v? If I take here, that is v plus del v by, v is varying with x, so del v by del x into delta x. That is again by Taylor series expansion. I can write that. I am not showing that again. So you have u becoming, you see here, u plus, u is varying with delta y, so u del u by del y, delta y. So what does this variation, cross velocity gradient, do? So it actually does angular deformation. So if you take that square again, you have O, A, B, C. So what happens? So the OA becomes OA prime and OB becomes OB prime. That is, OA as rotated by delta alpha and OB as rotated by delta gamma. Notice that this has rotated anti-clockwise and B has rotated, OB has rotated clockwise. Please notice that. So what is this distance? AA prime, that is, you have del V by del X delta X within the time this has happened, delta X within the time delta T. So this is similarly BB prime can be written as del U by del Y delta Y into delta T. Now angular velocity of OA, that is angular velocity of OA is omega OA is equal to limit as delta T tends to 0 delta alpha by delta T. See what is tan delta alpha? Tan delta alpha is opposite by adjacent, that is AA prime upon OA, that is AA prime is del V by del X delta T upon delta X. But for small angles, tan delta alpha is equal to delta alpha because delta alpha is very small. So now delta x gets cancelled out. So I can write limit at delta T tending to 0, delta alpha is now del V by del X delta T upon delta T. So that is nothing but my del V by del X. del v by del x. So now similarly let me do angular velocity of OB, that is omega OB equal to limit as delta t tends to 0 delta beta, sorry, this is not gamma, so this is delta beta by delta t. So that is, you have limit as delta t tends to 0, you have del u by del y into delta t upon delta t. How did I get this? Again, tan delta beta is equal to bb prime upon OB. bb prime is del u by del y delta t upon delta y. So that is, you get del u by del y delta t. That's what we have substituted, and we get here this as del u by del y. Now for the rotation to happen, if this has to rotate about an axis perpendicular to this paper like this, if it has to rotate, so it has to be omega z. If you just get to slides 1 second, to the slides, if you just get back to the computer, so omega z is the average of omega OA plus omega OB. But you see, if this is rotating counterclockwise, if I take it as positive, clockwise I should be taking it as negative. So omega OA would be positive, omega OB would be negative. So what would I get is omega z equal to, so if the counterclockwise is taken as positive, so you get omega z is equal to half of omega OA plus omega OB. So half of del V by del X minus del U by del Y. Del U by del Y. This is what you are going to get. So this is rotation along the z-axis. Now if you take del cross V, this is half of del cross V. If you take half of I j k del by del x, del by del y, del by del z, u v w. So you are going to get, now if you take rotation in the x direction, omega x, that is, you get half of del w by del y minus of del v by del z. And similarly, omega y is equal to minus, that is, del u by half of del u by del z, del u by del z minus del w by del x. So this is the physical understanding. How? So the point is, if we get back to slide, if we just say that omega is equal to I omega x plus j omega y plus k omega z is equal to half of del cross V. That's what. So rotation, vorticity. This I have to introduce what is called vorticity. Vorticity is equal to del cross V is equal to 2 omega. So that means the rotation, if getting back to slides, the fluid element will rotate about z-axis as undeformed block only when omega OA is equal to minus omega OB. That's why we took del u by del y equal to minus del v by del x, if you notice that. But if both are equal, then the rotation about the z-axis would be 0. So if del v by del x is equal to del u by del y equal to 0. So if rotation and vorticity are 0, the flow field is irrotational. Now angular deformation, if I take angular deformation, that is delta gamma is equal to delta alpha plus delta beta. That is, back to slides, if you just see this rotation, sorry, this angular deformation is delta alpha plus delta beta. So that is what we are trying to do here. So delta alpha plus delta beta means you get this as the rate of shear strain, or rate of shear strain is equal to gamma dot, that is gamma dot equal to limit as delta t tends to 0 delta gamma by delta t. So limit as delta t tends to 0, delta gamma is delta alpha by delta alpha plus delta beta. Delta alpha we have just derived, that is del v by del x delta t plus del u by del y delta t upon delta t. So you get gamma dot as del v by del x plus del u by del y. This is angular deformation. So we covered angular deformation and rotation. Now back to slides. So gamma dot equal to del u by del y plus del v by del x. Rate of angular deformation is related to corresponding shearing stress which causes the fluid element to change in shape. That is, if del u by del y is equal to minus del v by del x, so then rate of angular deformation is 0 and the element is simply rotating as an undeformed block. So that's what I told here also, that is, if del v by del x equal to del u by del y, then it is rotation would be 0, but rotation would exist if they are equal and minus sign is there. So that is, both should be rotating in the same direction. So if you have del u by del y minus del v by del x, then the rate of angular deformation is 0 and the element would be simply rotating as an undeformed block. So this is what we understood as angular deformation. So now coming back, this is incompressible fluid flow. Fluid elements may translate, distort, rotate, but they would not increase in their size or decrease in their size in volume. You may have del u by del x, but you may have countering del v by del y, which will make it del u by del x plus del v by del y equal to 0. So that is why it will not grow or shrink in volume, but in compressible fluid flow it will not only grow and shrink in volume but also translate, distort and rotate. So this is about incompressible and compressible fluid flow. So now if I just quickly take a recap, what did we do? We modeled translation, linear deformation, rotation and angular deformation. So we said that the linear deformation, just to summarize, you see, if you take velocity u varying in x, u is in the x direction, v in y, that is v is in the y direction, del w in del z, that is same velocity in the same direction, if that is changing, that would cause stretching. So we should be remembering that del u by del x is not velocity variation in x, it should be imagined as my fluid element is either stretching or getting compressed. Now if I write del v by del x or del v by del z, you see these are del u by del z or del u by del y, these are cross velocity gradients. Cross velocity gradients may result in either rotation or angular deformation, depending on how their values, whether they are positive, negative, whether they are equal to each other, that will decide whether they are getting rotated or deformation. Another important thing what I would like to tell you is that the velocity gradients are the ones which cause vorticity. That is, vorticity is nothing but can be imagined. This can be imagined as a rotation. So if you put really, getting back to slides, if you really put a shaft here, it has to rotate. That is, for example, if you take a blade, this is the blade and this is the fluid. Actually, there will be trailing tip vortices here. If you put your vorticity meter here, that is a small shaft with vanes that's going to rotate, that omega, this is omega z, that omega z is nothing but my half del v by del x minus del u by del y. You can either capture that rotational RPM and tell the omega z, or measure the velocity gradient and give the omega z. So much about the angular deformation. Now in the next classes we are going to write conservation of mass, momentum, energy. But when you do mass, momentum and energy, you are going to come across these gradients. You should be imagining them either stretching or compression. What we are saying is that if we take this blade and there would be trailing, these are called trailing tip vortices, trailing tip vortices. These trailing tip vortices can be imagined as nothing but my omega z. So that is half del v by del x minus del u by del z. You can either take that as a rotation or velocity gradients just by putting a shaft, measure the RPM, or you measure the gradients and get the rotation, either through these gradients or this rotation. Thank you.